I'm Professor John Frampton, Deputy Pro-Vice Chancellor at the University of Birmingham and Director of the China Institute. I'm delighted to welcome you to our 2021 China Institute Annual Li Siguang Lecture. This is our fourth annual lecture, named in honor of Li Siguang, who, as one of our first Chinese graduates, studied in the University School of Mining at the beginning of the 20th century. Li received his BSc in 1917 and his MSc in 1918, and was later awarded a doctorate from the University of Birmingham for his seminal studies following his return to China. Known as the father of Chinese geology, Li became a professor at Peking University and progressed to become an academician and vice president of the Chinese Academy of Sciences, along with many other influential positions. Our Li Siguang lectures are chosen to represent a wide range of disciplines that have relevance to our academic engagements with China. As was the case last year, we are once again presenting a lecture online, which is both a practical consequence of the current travel restrictions, but also enables us to bring together participants from across the world and to reach a truly global audience. Our speaker today is Yan Zheng from the Southern University of Science and Technology in Shenzhen, where she has been a professor since 2016. Professor Zheng is an internationally recognized expert on water resources and water quality, who has held major positions in both China and the United States, including professorships at Peking University, City University of New York, and Columbia University, from which she also obtained her PhD in marine geochemistry in 1999. Her significant influences include working for UNICEF in Bangladesh on water sanitation and being co-chair of the International Association of Hydrogeologists Managing Aquifer Recharge Commission. And her achievements have been recognized in her election both as Fellow of the Geological Society of America in 2010 and as a Fellow of the American Geophysical Union in September this year. In her lecture, Professor Zheng will provide an overview of the importance of restoring and sustaining groundwater as a resource to counter the effects of climate change and water exploitation in heavily populated regions, with a particular focus on the potential problem of contamination with substances such as arsenic. The timing of Professor Zheng's lecture couldn't be better, given the upcoming COP26 climate change conference that will take place in Glasgow at the beginning of November. Following the lecture, we will hold a panel discussion further to explore some of the topics introduced by Professor Zheng. The panel, which will be chaired by Iseult Lynch, the university's Professor of Environmental Nanosciences, also includes Stefan Krause, Professor of Ecohydrology and Biogeochemistry, Dr. Shirley Ye, Lecturer in Asian History, and Dr. Mike Jones, who is the Water Resources Modelling Lead for Thames Water. On behalf of the University of Birmingham's China Institute, it gives me great pleasure to pass over to Professor Yan Zheng for her to present her lecture entitled Enhancing Groundwater Sustainability for Climate Resilience Through Managed Aquifer Recharge.
Hello, everyone. This is Yan Zheng. I am a professor of environmental science and engineering at SUSTech Shenzhen. I am honored to be part of University of Birmingham's COP26 events and to give his China Institute Li Siguang Lecture 2021. Dr. Li is perhaps the most respected Chinese geologist with household name recognitions. Little known to many, Dr. Li received his undergraduate and graduate geology education in Birmingham more than a century ago. Today, I'm pleased to share with you how a little-known hydrogeological technique, managed aquifer recharge, or MAR, has helped to restore springs like this one, the #1 spring in China's spring city, Jinan. I open by highlighting the take-home message. Groundwater is being overexploited and polluted, but we need it more than ever to enhance climate resilience. When we use well water, it is a form of discharge. So are these beautiful ice sculptures formed naturally by discharging groundwater in Wisconsin. There are artesian fountains in Paris, initially installed by Sir Wallace, are another examples. The good news is that MAR offers help. This lecture illustrates how MAR has helped, why we need more of it. Groundwater is often forgotten with the traditional focus on the visible surface water in our mindset. This has led to a call to action by a group of concerned scientists. Groundwater sustainability should be incorporated into the United Nations 2030 agenda. I also thank Danita, UNICEF, UNESCO, National Geographic, and China's Most for funding projects that led to new knowledge and better practice of MAR, summarized in the SMART book available on UNESCO's website. Besides being Iseult that's easily forgotten, hardly anyone is taught about groundwater in school. So here are some numbers about groundwater to remember. The first number is 99. Groundwater makes up 99% of all liquid freshwater, and it is everywhere beneath us. The second number is about half. Groundwater discharges to surface water, making up about half of stream and river flows as base flow to sustain ecosystem, as shown by this cartoon to the right. Groundwater provides drinking water for almost half of the global population. Groundwater used for irrigation underpins almost half of global food production. The third number is 2. Groundwater currently provides more than 2 billion people worldwide for their basic water needs. What's concerning is, however, that almost always more water is extracted or discharged from fossil water aquifers than natural recharge can replenish. So, if we do not resolve this water imbalance, either by increasing recharge or reducing discharge, we are essentially using our children and grandchildren's water without even an IOU note. Ever since humans have repurposed land for our use from the natural conditions, groundwater recharge pattern has been affected. In rural settings, recharge from reservoir, farmland, orchards, fallow fields is not natural, so they are called incidental recharge to distinguish from managed recharge through infrastructure specifically built for recharge like this basin. Likewise, in cities, leaky sewer pipes are also incidental recharge. So to protect our groundwater from pollution by human activities, it is desirable to also manage this problem. At present, MAR does not include management of these incidental recharge yet. Instead, it refers to water resource infrastructure using basins, ditches, ponds, or wells to purposefully recharge water from a number of source water. The key here is that it is intended to be recovered for later use or for environmental benefits. For you to have a better idea what exactly MAR does, I'm sharing 3 examples from the 28 successful cases documented in this UNESCO MAR book. The location of the 28 MAR projects are mostly in areas with lowish annual mean precipitation. So clearly, hydrological scarcity is a driver for implementing MAR. Seasonal water scarcity, like this site in coastal Bangladesh, where it only gets monsoonal rain, is another motivating factor. So when I was with UNICEF, with Dhaka University and the Katia Water hydrogeologists, MicroMAR project was initiated in 2010 with 20 demonstration sites. Pond water was abundant in rainy season and is filtered through sand, then recharged using wells to what was brackish aquifer. The storage of fresh water is used for drinking. Although the amount of recharge is only hundreds of cubic meters a year, it is cheaper and more reliable than reverse osmosis, the best alternative. These water are extremely important for local villagers. Of course, risks like clogging and arsenic need to be managed. The second example is one of the oldest and largest MAR in Southern California, where all water is managed in this coastal watershed by the Orange County Water District. Established by the California State Legislature through an act in 1933, there are several components of the LCWD MAR. In the higher elevation area, Santa Ana River and nearby recharge basins add water to the aquifer. Closer to the coast, wells inject treated wastewater to prevent seawater intrusion. Because the source water is blended river flow and recycled water, contaminants of emerging concern are new water quality challenges needing attention. The third example is one in Jiaodong Peninsula, where underground dam provides an effective barrier for seawater intrusion and restore groundwater and also base flow in the river. There are many of such MAR infrastructure, so only one of them, located on the Bailisa River, is shown. Professor Weiping Wang of University of Jinan worked on this. He is in the picture when the dam was constructed in the late 1980s, intended to mitigate shortage of irrigation water due to severe drought then. What's noteworthy is that the cost of the recovered water is extremely low. Which leads me to cost effectiveness MAR. The MAR book has a synthesis chapter written by Andrew Ross, an economist, that took a close look at this. It is notable when the recycled water is used for MAR, it is more expensive than natural water source. Another synthesis chapter written by myself assessed the sustainability of these 28 MAR schemes. It is good to see that MAR is a sustainable technology. An indication is that the recovered water is more or less the same with the purposefully recharged water, so water balance is maintained. We do, however, need to pay attention to the high energy intensity associated with recycled water. These examples show that MAR has many utilities, but can it fix groundwater depletion at large scale? For example, the North China Plain. NCP is one of the global hotspots of very high groundwater extraction, estimated to be in negatives 10 to 15 millimeter per year. Pumping so much water out has led to substantial groundwater level decline, more than 30 meters in a few places. Sucking so much water out is making the land to sink, with more than 3 meters of land subsidence, making it more vulnerable to storm surges with sea level rise anticipated with climate change. The majority of groundwater extracted is for irrigation. China Geological Survey has estimated that in 2010, the over-extracted amount is about 4 billion cubic meters each year because we need water to grow food. Without food, there will be famine. It is a tough situation. Then came the colossal south to north water diversion, transferring a planned 18 billion cubic meter water from the Yangtze River to the Hai River Basin, where the North China Plain is within. Because the planned 18, and in reality, the transferred 10 is more than 4. Presumably, if people could switch this new water, the over-extraction of groundwater can immediately stop. Although this new transferred water is a relief, the reality is more complicated, mainly because where the groundwater has been depleted, notably along the western mountain front, we still need to continue to extract water from wells for irrigation until new water distribution network is in place. But the spatial pattern of net irrigation water use has never been quantified. With funding from DANITA, our project team at the Danish Geological Survey, Dr. Julian Cochet worked with Professor Simon Steitzen and colleagues to estimate irrigation and other water demands across the Hai River Basin. Irrigation use the most water each year. 126 millimeter water, or 15 billion cubic meter, is sent back to the air. This is more than the south to north annual transfer amount, about 10. Fortunately, with all water available, there's still leftover, so about 1 billion cubic meter water has been used for MAR since 2015. A location where this MAR took place is the Taobai River of Beijing. It was dry because groundwater feeding to it was depleted. Now it is flowing with the new south to north water. Our project team at the Beijing Water Science and Technology, Dr. Binghua Li and colleagues have experimented the alternating wet and dry recharge methods for more recharge and better quality water. The good news is that groundwater storage has increased by 0.27 billion cubic meter. So with more MAR, the groundwater will be brought into balance in the future. If you recall my cover slide, it turns out the in-channel MAR at Yufu River since 2015 has recharged 0.15 billion cubic meter water, crucial in storation of culturally significant springs in Jinan. Our project team at Jinan University, Professor Weiping Wang and students, have examined the water balance of the karstic aquifer that feeds these springs using local reservoir, Yellow River water, and south to north transfer water. This also ensures a resilient drinking water supply of Jinan City with 9 million people. A second opportunity for MAR in NCP is to utilize the wasted floodwater and the ever-increasing amounts of treated wastewater. In 2015, only about 1/3 of domestic wastewater is treated for ecological use in dried rivers in Hai River Basin. By 2020, China has completed a major wastewater treatment revolution. Now nearly all domestic wastewater is treated and used to restore flow. So currently, there's a lot of incidental recharge of this recycled wastewater, and it would be very good that this is managed. So my team look at water quality risk associated with recycled water use during recharge, either incidental or managed. This is because one of the major advantages of MAR is its ability to use nature, such as soil, aquifer, sediment, to naturally attenuate contaminants, purifying our water at no additional costs. Arsenic is a toxic element, and US researchers have reported that in Orange County, which I've shown earlier, injection of treated wastewater to brackish aquifers to stop seawater intrusion has caused arsenic mobilization. So when master student Yu Xiayang took reclaimed water flowing in Beiying River of Beijing and mixed with sediment from North China Plain, we only observed a tiny release of arsenic. So this is very encouraging. Former PhD student Men Ma and postdoc Yunjie Ma conducted field experiment and a lab experiment to examine to what extent antibiotics, a class of contaminants of emerging concern, is biograded in the soil aquifer system naturally. Our findings indicate that sulfonamide antibiotics do not fully transform to carbon dioxide quickly. It tends to become intermediates and at present mostly unknown products. So this is a tough situation and something we want to continue to work on to find solutions. I hope by now you are getting to know MAR a little better. So these are the 8 things that MAR can do. Top and clockwise, increase water security, improve water quality, provide ecosystem benefits and seawater intrusion barrier, improve groundwater sustainability, enhance public confidence from toilet to tap, turn wasted or wastewater into a resource, turn low-value water into high-value supplies. I really hope that in the next decades, people around the world will use a series of MAR technologies to become smart. This can resolve the mismatch of space and time between water demand and supply. And to achieve this, we need better regulatory framework, and we need to stay vigilant against old and new water quality threats to ensure groundwater sustainability. Thank you for your attention. And I would like to thank my collaborators and encourage more young people to study groundwater as a subject. Please send your questions and comments by email. To honor Dr. Li Siguang, this is his brief bio in Chinese. His 1918 master's thesis is a masterpiece and is entitled The Geology of China. And in 1952, he was named the founding minister of the Ministry of Geology. We have many wonderful geologists to be grateful for to allow us to adapt to climate change. Thank you.
Thank you, Yan, for the wonderful and informative presentation, and welcome to our panel discussion. Let me just introduce myself and the rest of the panelists very briefly, and then we'll continue with our discussion. So I'm Iseult Lynch. I'm a professor of Environmental Nanosciences at the University of Birmingham. My research looks at the fate and behavior of very small particles, typically engineered ones, but also anthropogenic ones, and how they interact with the environment and with humans. And I fully agree with Yan that we really do need to learn to look at chemicals as a whole rather than one at a time. So, yeah.
I'm Stefan Krause, and I'm a professor for Ecohydrology and Biogeochemistry at the University of Birmingham, where I lead the Water Challenges theme at the Institute of Global Innovation. A lot of my research is addressing integrated surface water and groundwater challenges, like the pollution of surface waters and groundwaters with emerging contaminants and how they interact with legacy contaminants in the environment.
Hi, my name is Shirley Ye. I'm a lecturer in Asian history. I'm a historian of modern China and the world. Some of my research has looked at the role that multinational actors, engineers, diplomats, have together negotiated and negotiated the river conservancy organizations in China's treaty ports, as well as the Grand Canal in the early part of the 20th century.
I'm Mike Jones. I'm the Water Resources Modelling Lead at Thames Water. I'm a hydrogeologist by background, but my role at Thames Water isn't just about groundwater. It's about understanding all our water resource assets, as we describe them, understanding their performance, particularly under drought conditions, but making sure that those assets are able to provide a resilient water supply for our customers now and into the long-term future.
Oh, hi, my name is Yan Zheng. I'm a professor at the School of Environmental Science Engineering at SUSTech, Shenzhen. I'm very honored and pleased to be in this panel discussion.
Welcome all, and looking forward to a very interesting discussion. So I'm going to first turn to Stefan and just ask for your first reflections on Yan's presentation.
Yeah, thank you very much, Iseult, and hello everyone. It was fantastic to follow your presentation, Yan, and I was really intrigued by, in particular, the controversy that you did show towards the end as well, in looking into potential unintended consequences with the focus on not trading of water quantity for water quality challenges, really being concerned about the impact managed aquifer recharge could have on the release of geological contaminants like arsenic, or really new, more emerging contaminants like, in that case, antibiotics. And that resonates with a lot of research that is ongoing, of course, in groups around the world of trying to prevent these unintended consequences, in particular when it comes to emerging contaminants that we don't manage to strip out of wastewater that well. That's with regard to pharmaceuticals. And one thing we are particularly interested in, of course, as well, microplastics and nanoplastics and all the potential release of additives from when they reach the soils, the groundwater as a really precious resource. So it was really great to see that there's quite a lot of thought on how we can prevent these unintended consequences, and it's a bit daunting almost to understand what a huge need for future research there still is, given this real cocktail of emerging pollutants. And one thing I think we start to understand, of course, that often it's the breakdown products of that emerging contaminants that give us unintended consequences. So I'm really very happy to see that these are things that are taken into account, and of course interested to learn more as well of how, for some of this really large scale endeavors like the South-North water divide, etc. It's a very different scale than managed aquifer recharge schemes we see in the UK. How this can be assured at scales like that.
Shirley, I think that connects then to some of the ideas that you work with, and this sort of historical timescale and how things have changed over time. Is there anything you would like to reflect on in that direction in terms of changes in water management and water infrastructure?
Thank you so much for having me on this panel. In many ways, I'm the outlier of this panel. I'm the non-scientist here, but yeah, and I found your lecture absolutely fascinating from a humanities and historical point of view. I saw that there were many parallels between our contemporary moment and the early 20th century and late 19th century, which is my period of study. And what I was really struck by was the aspect of international collaboration among scientists across nationalities, the collaborations across academic institutions and also international bodies. But I mean, one of the kind of differences between the early 20th century and our contemporary moment is that engineers and government officials were primarily concerned with the problem of managing China's sorrow, which is what the Yellow River have been called as a result of successive flood disasters throughout the 19th century and into the early 20th century, not just the Yellow River, but also tributaries of the Yellow River, including the High River, which Yan Yan spoke about in her lecture. So kind of the focus of water management in the early 20th century was more kind of societal. It was disaster management, whereas today we're looking at a really, really different kind of crisis, which is water pollution.
Super. Thank you, Shirley. Mike, you're coming at the question and the topic from a much more practical industrial perspective. So it would be super to hear your initial reflections as well, please.
Yes, thanks, Iseult. Yan, great talk. I guess in a short space of time, you've given us a really great introduction to people who don't know much about managed aquifer recharge and the sort of the enormous range of potential applications that MAR can be used for in terms of environmental restoration, water supply, prevention of saline intrusion, and also the scales as well, from the micro MAR in Bangladesh to the potential use of MAR in the North China Plain examples you talked about, and the scale of those that you're talking about is like, wow. Coming back to Stefan's point, I've just thought about some of the numbers that you've mentioned. So I think the transfer from south to north that you talked about, that 18 billion meters cubed per year. So that's 25 times bigger than London's water supply. It's just, but there was some other figures. The depletion of groundwater, the over abstraction. I think that was about 5 times the size of London's water supply, and so the role that MAR's got to play in trying to mitigate some of those challenges that we put ourselves in with over abstraction of groundwater and maybe some of the contamination issues. It's how MAR can play a role in a more conjunctive use. A conjunctive water supply is what really struck me from your talk, and trying to bring together groundwater abstraction with transfers from other basins and using some of that water for managed aquifer recharge. The potential on that scale is absolutely enormous. But it's, as Stefan said already, it puts it into context with what we currently do in the UK. The scale is just so different. I guess the other thing that struck me as well is something really about how what we need to do as maybe as a hydrogeological community, but also a wider international community in trying to promote the use of MAR and really the regulations and the overall governance that needs to be in place to make sure that MAR can be facilitated. And you just wonder how we got into this situation with a lot of groundwater over abstraction, groundwater pollution. Does that mean it's all been going so horribly wrong with the regulation, and what we need to do to put it right to make MAR deliver on the potential that it really does have?
Super. Thank you so much. There's lots to unpick there. I think I'm going to hand back to Yan and ask maybe if you're happy to expand a little more on the role of international cooperation. And you gave some really excellent examples of that and where you think might be the important next steps in terms of developing this international level cooperation on managed aquifer recharge.
Yes, thank you all for your kind words. And this is a very interesting endeavor for me. In terms of international cooperation, I think we can do more to bring people on the same page regarding, I think, water quality. Because when I was working on that UNESCO MAR book and spent a lot of time thinking about what groundwater sustainability means and what criteria we should have to ensure groundwater sustainability, it actually basically we need to ensure groundwater quality's integrity in order to not trading quantity for quality. So this is to me the foremost important thing. But when it comes to this, it becomes a little bit tricky, because there is no agreed upon way as to what ground quality should be. They vary from places to places, they vary naturally. And depending on the purpose of how we want to use groundwater, it can be different, right? If you want to use it for drinking, you probably want to manage it a little differently. If it's going to be used for irrigation, it'll meet different sets of standards or for industrial cooling and all ecological water. So we haven't really thought about that. We haven't really discussed it. So I think it would be really great if institutions like UNESCO, as they are already involved, and IAH, which is International Association of Hydrogeologists, continue this discussion, organize experts, and then think through this. And then perhaps like WHO, they put out guidelines for drinking water quality. We have nothing like that. Yeah, what should we have for groundwater quality guidelines from technical perspective? I think we need to sort that out. Because if you don't sort it out, and just to address a little bit of all of your questions, it's very worrisome. We have these old and new water quality threats. Stefan was pointing out that I mean, I live in this world. I know it's very tough. And Mike also was pointing out that, you know, have we done everything wrong from the very beginning? Because no one was looking after groundwater. So we wound up in this place at first place. And then all the Shirley's perspective, I think it's because in the past, we just look at the surface, right? We have these floods, let's deal with them, that's killing people, ruining properties. We just haven't thought about it very much. So, but it's, I mean, I'm hopeful, it's never too late. I do think international organization has a role to play, even though every country, every place is different. But we can provide perhaps the much needed technical support and some ethic guidance as to what would be the right thing to do, both to the people and to the groundwater system.
Thank you. Stefan, do you want to add on to that, and you know, from where academics can feed into the processes?
Thank you, Iseult. Yeah, if I can come in there very quickly, I totally agree with what Jan just said about the role and the importance of international networks to actually sustain this collaborations. As you mentioned, Jan, the conditions are so vastly different. So it's really difficult to define standards, to define what we want to achieve. And we see that through, you mentioned UNESCO and IAH, and we see that through interactions with UNESCO. We hold a water share for UNESCO in the University of Birmingham, which is held by Professor David Hanna, and we are running the UNESCO Unitwin network on ecological interfaces. And that really, what you said resonates with that. We see that when we manage groundwater and surface water, or we endeavor to manage groundwater and surface water in an integrated way, there are this really vast global differences. And one thing I think we as a community started to understand a while ago, now need to implement, is that whatever decisions we make and whatever we do to groundwater has a lasting impact. And that really links to what Mike said. Did we get it all wrong quite a while ago? And we still see it, of course, right? And that's where I think it's really important, all that work you and others have done on looking into the potential risk of contaminating really one of our most precious natural resources, groundwater, that would have effects lasting for generations, and where we still need to understand so much of how some emerging contaminants, which we not even see yet having reached the groundwater. We just know they are on the transfer down there, like we have been worrying about the time bomb of nitrate in groundwater, right? That we started to see in the last decades. We now wait for the more particulate contaminants reaching down there, and I think this time lag is something that we need to understand better, and can, I think, only efficiently understand. I totally agree there with you. And efficient international collaboration, we need to have this networks facilitated through UNESCO, IEH as a backbone to actually support this lasting collaborations.
Super. And Mike, can I come to you then to sort of pick up on the role of regulation and regulatory guidance in all of this?
So I guess my perspective on the regulatory frameworks that exist, they're obviously, as Jan has said already, different in different parts of the world. But I guess I do wonder about why regulation evolves the way it has. And Jan, you mentioned in your talk about effectively groundwater being out of sight and out of mind. And maybe there's something about education, about, not only at a university level, but educating young people, raising awareness of groundwater, what is beneath their feet. And I guess I say that because I do worry a little bit, at least, about whether people who are set in regulatory frameworks now actually understand enough about groundwater to enable them really to put appropriate and effective regulation in place. Whether that's true or not, I don't know. But for me, there's that whole education piece that needs to be strengthened, that regulation that needs to be there to support more is set on some really good, strong foundations.
Super. Thank you, Mike. I'm just going to pass to Shirley now as well to sort of reflect on that and on the historical and future implications of regulations that we put in place now.
Thank you so much, Mike. I found your comments really, really informative, and as well as Stefan. I guess what I see, I study I study the contestation over water management in the early 20th century, and I guess what I'm struck by is, what Yan started her lecture with, which was the tragedy of the commons, right? Like, who has is access to clean water, to clean groundwater, a human right? Is it the right of the people who inhabit that land, or is it is it right that regulatory bodies and frameworks who come from outside of that locality come in and impose their own their own globalized norms and techniques and understandings of how that groundwater should be extracted and distributed and utilized. And I think that contestation is really, really interesting, and it's probably kind of at the heart of governance, right? At the heart of governmental legitimacy, right? What role does the regulatory framework, whether it's at the urban level or the township level, whether it's at the provincial or county level, at the level of the nation state, and to what degree do locals, right? To what degree can they leverage international norms of access to water and access to a certain quality of water, right? For their own for their own livelihoods, right? So I think, I think that's really, really interesting. I mean, so the problem of regulation is a really important social question.
Yeah. Just picking up, thank you, Shirley, and just picking up on Mike's point then about the need for increased awareness and understanding of groundwater and its important role. Would any of you like to sort of reflect on the transition in the last while, from managing of surface water now to managing of groundwater and the interplay between those two? Maybe we come to you first, Yan.
Oh, okay. Yeah, it was very interesting to hear everyone's perspective. This is actually a really new field. There is a paper I think just came out a couple of years ago by law professor in California, Owen. He wrote about how the U.S. groundwater law came about, and it's just I don't know. A really interesting mixed bag of everything, for lack of better words. Yeah. So basically, we haven't been very coherent about how to govern groundwater, and that seems to be the case in many countries. Talking to John Cherry, and he's initiated now this groundwater project, which addresses this very important education and outreach problem. The groundwater project wanted to make groundwater knowledge available for free to anyone who cares to study. But it is fairly technical. This is aimed at university level, I think. But it's still very much necessary. I think, I don't know. I mean, I think I'm glad there are more people from different disciplines are becoming interested in groundwater. And because let's face it, like we all have our own limitations. I study groundwater chemistry. I probably look at everything from groundwater chemistry perspective. And then people from different perspectives, they'll look at it from different perspectives. And I also think we need to sort out the big ethics issue first. What are we trying to protect? Are we trying to protect people's health, people's property rights, or are we protecting ecosystem? Are we trying to protect groundwater for the sake of groundwater? I don't even think we agree. We don't really have, and if your values do not agree and are aligned, and I think this is where the international discussions are going to be helpful, because we can then agree on a set of principles, if you wish, as to how we should move forward, and that should not be in conflict with local people's value and culture and history and all of that. So it's a very complicated task. And that being said, I also feel time is running out. We shouldn't take forever to do this. If we really want to protect groundwater, we probably should do something in the next decade. We don't want to wait until 2100 and with everything already like transferred to downward and polluted, and it'll be kind of sad. So I think we need to, it may be worthwhile to take advantage of next year, 2022, the year of groundwater, to initiate something. And let's say by 2030, by the time with SDGs, the timeline, we need to come out with something that will kind of guide sort of human and groundwater relationship, clarify that. That'll be very helpful. Perfect. So thank you.
Mike, just building on that then, Mike, can I come to you to reflect also on some of the different uses of groundwater? And I know, for example, one of the projects that you manage is sort of a reserve for in the case of water shortage. So, how we might build that into our overarching governance and thinking about protection of groundwater in the long term.
Yes, I guess from a Thames Water perspective, we have a very large managed aquifer recharge scheme called the North London Artificial Recharge Scheme. It's the largest operational scheme in the UK. But just thinking about the numbers I mentioned earlier on, NLARS, as we call it, only provides at peak supply capability about 10% of London's water supply. So compared with some of the things that you've been talking about, Jan, it's tiny. It's tiny. And in the UK, our approach to regulation and planning is very long term. We're required to look out to the year 2100 by our regulators and look at our supply demand balance and what it is we need to do to try and make sure that customers' demand for water can be met. Obviously, balancing with demand management, implementing water efficiency measures, but also delivering new water resource schemes. And I guess it's interesting to note from a UK perspective that there are very few managed aquifer recharge schemes in the plan. And what there are really very, very small. So we're talking about in London, the North London Artificial Recharge Scheme. We talk about it in megalitres per day, so millions of litres per day, not in meters cubed, unfortunately. But it's at peak, it's around about 200 million litres per day. But we're talking about developing schemes now that might only be delivering 5 million litres per day, maybe 10 megalitres a day, so that they are really, really tiny. And I guess it's interesting just to link it back to the way, I suppose, regulations develop and how how water resource management plan decisions are driven, there's quite a lot of NGO stakeholder inputs, which are coming to the fore much more in the UK now, looking at it from an environmental ambition perspective. And it's an interesting contrast. There's a drive now, certainly not to increase groundwater abstraction and it become unsustainable, but it's not to promote managed aquifer recharge. The aspiration is more to reduce groundwater abstraction, to protect sensitive, vulnerable rivers, basically, in streams. But then the solution to cover off those reductions is to bring in water from other catchments. So transfers from the Severn catchment into the Thames catchment, perhaps a lot more effluent reuse. So there is this sense of conjunctive use of different options, but unfortunately MAR isn't playing much of a role. And it feels like there are the vulnerabilities in taking those decisions about transfers from other catchments in terms of climate change resilience. But also, I guess, if we're not actively using groundwater as much, do we lose a little bit of the ability to have planned conjunctive use? It's interesting what you described in China, and is very much going the other way. It's to make MAR a key part of longer term water resource management planning, whereas in the UK, we're taking perhaps a backward step. Really, I'm not quite sure. It's an interesting sort of perspective. But I think about some of those decisions or aspirations that are driven by NGOs, members of the public, basically. I think Shirley, you had a perspective on how decisions are driven, perhaps by different stakeholder groups.
So thank you very much all for the wonderful discussion. I'm conscious that we're coming close to the end of our allotted time. So perhaps I could ask you each just to reflect then on what you think are the main challenges going forward. So I might pass to you first, Stefan, please.
Thank you, Iseult. I think what the discussion and Jan's presentation has shown really nicely is how important it is to manage groundwater and surface water in an integrated way. And MAR is a fantastic example for that need. And as Jan alluded just now, there's been groundwater regulation has been lagging behind the regulation of surface waters for a while, not just in the US and the UK and Europe, with a groundwater directive lagging time-wise behind the Water Framework Directive. We are facing very similar challenges. And if we have seen one thing in the last couple of years with experiencing a pan-European groundwater drought, having experienced some severe groundwater flooding in the UK a couple of years ago, we really start to understand that we can face that challenges and fight that battles for water quantity and quality only in an integrated way, where we are looking into solutions that actually are integrating both the environmental and human health and economic impacts of our solutions to these challenges, both for surface water and groundwater, in an integrated way.
Super. Yan, please.
Yeah, thank you. It's been really, really interesting. And I think these answers lie in, I agree with like a lot of education. So I think the hydrogeologists working in this field, we really need to do more to reach out to the public. And speaking of the contrast between the UK and China and other places, I think humans are always just contracting. We are constantly revising what we do and think what we do now is better than what we have before. Perhaps it is not. So, but I remain hopeful. I think, as Stefan hinted on, and we eventually learn the lessons from the history, and I hope Shirley would agree. And if we have the knowledge properly sort of shared in a sound way with stakeholders, I think most of the times we make the right decision, and that's right, at least for the time. But with groundwater, I think a word of caution I would like to say at this time is that we are not thinking about the future generation enough. So I think when we think about how to manage it, we need to think about perhaps more the future generations need, which is where I think the quality problem really comes in. Not only you have to care about the groundwater quality now, you have to think about what might happen over, let's say, at least next 50 years. So thank you all for a very interesting discussion. I really enjoyed this.
Perfect, thank you. Mike, please.
I guess for me, there's a big picture view really about whether MAR can be, a viable application in a rather uncertain climate future. MAR in itself, is a technique that has really potentially very good climate resilient credentials. But I guess the key thing of MAR is having a reliable and viable and appropriate quality source of recharge water. And I just think, focusing on that a little bit more in a climate future, can we be assured that our source of recharge water is there when we want it, and there where we need it? As you said, Iseult, earlier on, from a London perspective, Thames Water has a MAR scheme that's very much focused on a strategic drought resource. It doesn't get used all that often, but in other applications, MAR is going to be used on an annual basis. It's like, well, can we make sure that the recharge water is always there to make sure the scheme is topped up for more immediate use? So that's the sort of challenge that I think about from a big picture point of view. And I guess then a lot of the detail needs to come in the design of the schemes to make sure that we're looking at the right type of recharge water, the right type of quality, making sure that our recharge is, when it gets into the aquifer, does it remain there? It's largely about the residence time. How long does it stay in the aquifer to deliver beneficial use? And there's a lot of different design components, the quality and the quantity side of things, that need to come together. And it's like I can imagine, a good challenge for the international hydrogeological community would be some sort of design standard. It isn't only about the education, it isn't only about the governance, it's about design standards as well. So really a very interesting sort of challenge for the future for hydrogeologists, maybe.
Super, super. Shirley, any last thoughts?
So I'm not sure I have much more to add to what everyone has just said, but I will say that, water is so fundamental to life, right? Water, without water, we cannot live, right? Without water, humans cannot live. Without water, non-human life cannot exist. And I think that, I would agree with Mike that there needs to be greater education about the importance of groundwater and the importance of, having an integrated perspective, as Stefan said earlier, in bridging the languages of the humanities and the sciences, and creating common language and hopefully common shared values through which we can kind of negotiate our future.
Perfect.
Yeah.
Thank you very much, Shirley, and all. And I think this has been a really interesting discussion and a very nice lead in, I think, to the year of groundwater. But just before I let you go, I'm going to just throw out one last question to just see what you think. And I know many of you have worked with arsenic and some of us are working with microplastics. So just to see which you think are the biggest threat going forward, the legacy pollutants or the emerging pollutants. So Stefan first.
I don't have a short answer. I think the question is where and when, I guess. And one thing that rose from the discussion is that there's really often a legacy effect, and in particular for many of the emerging contaminants, we don't know what that legacy is yet. And coming to arsenic, there are solutions to arsenic challenges, but the accessibility to them is probably like with vaccines. There are richer parts in the world that have much better accessibility to that solutions than some parts that are very heavily affected by arsenic pollution and have less access and also less awareness and knowledge of the problem.
Perfect. Mike, please.
I guess legacy issues. You know, that we know quite a lot about them. Our knowledge is improving. We understand how we might be able to deal with them. But I guess it's sometimes you get a bit of a surprise. You find things that you don't expect to find. You might be monitoring for those potential contaminants, but you might not expect to see them. So it's those surprises, like the arsenic example. It's like, you know, you find it when we found it when we least expected it. So you've got to keep looking. But I guess the other part of the picture, the emerging pollutants, I guess the more you look, the more you find. And I guess we don't know about some of these problems because we're not looking for them in sufficient detail and perhaps at the right times and in the right locations. So, you know, it's back to Stefan's. There is no short answer. We've just got to keep on looking and understand, you know, understanding the problem and treating them as a challenge that we're looking for solutions to deliver on them, to make sure they're not showstoppers, really.
Perfect. And Yan, please.
I agree with what's being said. But I think if I could take a step back and look at these emerging pollutants, they are made by people, right? They are by and large synthetic chemicals that are needed for other parts of our lifestyle. And I was actually just at an ecotoxicology meeting yesterday, and there are these people who study toxicity of these, I don't know, close to 100,000 chemicals that are in common use today. So I feel like we groundwater people are dealing with this consequence because everything goes down. Groundwater is the grave. Sooner or later, we find them. And I will not be surprised that we will find everything if we look. So, I mean, we can still try to resolve this from technology. And the main thing, the talk I gave yesterday, I mainly pleaded these people, toxicologists, to develop a tool that can tell us the toxicity of the water. I mean, the mixture, not just this one compound. You can do a non-target screening, and then boom, you have like 5,000 chemicals in your water. That's very common these days. It's not uncommon. So every time I drink water, I'm drinking thousands of synthetic chemicals. And you know, yes, access will be an issue. So when we have a handle on these, it's more or less when we figured out how to remove them, how to further purify them with other chemicals we make, so materials we make. So so it goes back to the question, what are we trying to protect? So we haven't really sorted that out. Again, people with more money, more resources, more command with technology are better at protecting themselves than people who will not have access. So this creates a really great environmental justice issue. So that's my perspective. And I hope we don't need to make so many chemicals, but that's what chemistry is all about. So.
Perfect.
Thank you.
Super. Thank you very much. So lots of big challenges still to be addressed, and hopefully the year of groundwater will help to raise the awareness that's needed and to see real progress in all of these issues. Thank you very much to all of the panelists. I've certainly enjoyed hosting the discussion, and I hope you all have enjoyed participating as well. So thank you very much, everyone, and thank you all for listening.
I'm sure you will agree that this has been a highly informative and stimulating lecture and discussion, providing us all with insight into the ways in which the collective research efforts of great minds around the world can be brought to bear to ensure precious resource sustainability alongside protection of the environment. A huge thank you to Professor Zheng for her excellent presentation, which was perfect for an audience with a broad range of interests and understanding, and gave a real sense of the way in which research collaboration across international borders can be so effective in finding solutions to the big challenges of our time. I'd also like to thank our panel for their participation and lively, engaging discussion, bringing further insight from their own specialisms and experience. Special thank you, of course, to the behind-the-scenes colleagues who have worked over many months to make this event possible, including Nina Morris and Shruti Doshi from the China Institute team, as well as Creative Media, who brought together the various strands to give us a very polished production for our global audience. Finally, thank you to everyone who has joined us online, either in the UK or around the world. We hope you've enjoyed this event as much as we have enjoyed participating in it, and I hope that you will seek out the University of Birmingham China Institute and its work through our website and various social media channels. Thank you.